Alright, so just a little bit more on optimization. So what do we know about optimization? Well, it's an opportunity for us to find the best or the worst for a given situation. So we might often try and find, say, the maximum profit. So given a function, can we find a way in order to maximize the amount of money we're making? The opposite to that might be trying to minimize wastage. When it comes to optimization, we need to really include all of the possible options in our domain, so we don't always just assume it's going to be the minimum or maximum. We really need to explore the boundaries. So our advice is always sketch. It really helps us to know where to look. So for this particular example, we've got someone standing on a cliff 40 meters above the sea level. They throw a stone. The equation of the stone traveling is y equals 40 plus 5x minus x squared. They tell us that the height of the stone above sea level is y, and x is the horizontal distance, both in meters. So what do they want? They want to know the maximum height above the sea level. So they say greatest, we interpret that as maximum. So this is one of those opportunities for us to actually explore where the maximum is. So all I've done here is I've taken that equation or that function and whacked it into a graphing program. So we can see it's going to be around this point. Now if you have your graphing calculator, for example, it will tell you that point fairly easily. You might even estimate it by just using your trace function, but we want to know the exact point, and quite often in your exams they want you to prove it algebraically. So what could we do? Well, the beautiful thing about optimization is that we know derivatives will tell us the rate of change, and at the maximum point the rate of change is 0, as in the gradient is 0. So if we know the function, we can do the derivative and sub in 0, and we will be able to find by a bit of rearranging that the point where we hit that gradient of 0, or the rate of change of 0, will be where x is 2.5, and we can see that lines up fairly nicely. Whoops, that's 3, sorry, 2.5 is about here. Alright, so is that the answer to the question? No. We've only found an x value, so we've found the horizontal distance, but this particular question asks us for the vertical, so the height above sea level. So we know what x is. We can sub x back into our original equation, and that will tell us our y value, which in this case was the vertical height above sea level. Okay, so original equation, sub in out 2.5, and in this case it's telling us that the greatest height above sea level is 46.25. Now if you're doing Maths B in Queensland, a modelling problem solving criteria will talk about assumptions and their effects. So in this particular case, if you've ever been to the sea, you will know that the sea level changes with the waves. So we've had to assume that the sea level is not changing. Okay, so we would imagine that as the height comes up, so our difference would change. So we've assumed the sea level is constant. We've also assumed that those lovely onshore winds would not change the path of our rock. Okay, so the assumption is those, the effects therefore would definitely impact on our model. Okay, so in that case we're looking at a question, modeling and problem solving for Maths B, probably around a sea level.